Okay, everyone, welcome to lecture 3. And this is going to be on section 2.4 from your textbook, which is on complex numbers. Okay, so first, to motivate this, let's think about solving a particular equation. Let's say I have x squared minus 1 is equal to 0, and I want to solve that particular equation. We will talk more about this later when we get to quadratic equations, but you may remember how to do this. Actually, there's a couple ways you could do this, right? You could factor the left-hand side and say x squared minus 1 is a difference of squares, so it factors into x plus 1 times x minus 1 equals 0. And then if I have something times something equals 0, the first factor could equal 0, or the second factor could equal 0. And if I solve for x in the first equation, I'm going to get x is equal to negative 1. And if I solve for x in the second equation, I get x is equal to positive 1. So it has two solutions, right? X could be negative 1 or x could be positive 1. Another way you could have done this problem is you could have brought the constant to the other side and you isolate the x squared, so I have x squared is equal to 1. And now to get x, we take the square root of both sides. And you have to remember that it's going to be plus or minus, right? So let me remind you of this on the side over here. So if I have x squared is equal to k, then x is going to be plus or minus the square root of k. Right? So I can take the square root of both sides, but I have to account for the fact that it can be positive or negative. Because if you substitute positive square root of k back in, and you square it, you get k. Or if you substitute negative square root of k back in for x and you square it, you're still going to get k, right? So there's two solutions. So in this case, x is going to be plus or minus, and then of course the square root of 1 is just 1. So I get exactly the same solution, right? Just another way of solving that particular problem. But let me make a small change to the equation. Let's say it's this. Let's say I want to solve x squared plus 1 equals 0. Well, I can't factor the left-hand side, right? So that doesn't work. Let me try the second technique. Let me just isolate the x squared, so I'll move the negative 1 to the other side. Or in other words, I'll get rid of the 1 by subtracting 1 from both sides. So basically, a negative 1 appears on the other side. And now, if I try to take the square root of both sides, and again, I have to assume it's plus or minus, I have a problem here, right? Because what we say in math is that there is no real number, right? There's no real number answer when I take the square root of a negative number. So how do I take a square root of a negative number? Well, there is no answer if we're dealing just with real numbers. So here's where we have to introduce a new set of numbers called imaginary numbers. And then eventually, when we combine the real numbers with the imaginary numbers, we get what's called the complex numbers. So by convention, people give this a name. They call the square root of negative 1, they call that I. Actually, some scientists, usually engineers, may also call it J, but typically mathematicians and physicists call it I. So the key thing here is, by definition, so I'll put the key, is that the square root of negative 1, that equals I, which is an imaginary number. And this is going to allow us to do many more problems. By the way, if I square I, here's another way of writing the key here. If I square both sides of that, I'm going to get I squared is equal to -1. So that's another way of saying the same thing. Square root of -1 is I, or I squared is equal to -1. Okay, so let's see how this is going to help us. Let's say I'm asked to simplify square root of -64. Okay, so normally if I'm just dealing with real numbers, there's no answer, right? There is no real number such that when I take the square root of -64, I get some answer. But if we include imaginary numbers and complex numbers, I can do this. In fact, you can think of this as, I'll kind of split this up as the square root of 64 times the square root of -1. Right? I'm using the square root of a times b equals the square root of a times the square root of b. Just some of my rules for radicals. And we just said that the square root of -1, we're going to call that I. So this is going to be equal to, well, square root of 64, since 64 is a perfect square, this is simply equal to 8. And then square root of -1 is I. So square root of -64 is 8I. Okay? And again, this is what we call an imaginary number. The part that contains the I is the imaginary part. All right, so what is a complex number? Well, a complex number basically is the sum of a real number part and an imaginary part. So it's the sum of a real number and an imaginary number. So a complex number is the sum of a real number and an imaginary number. So for example, if I have, say, 7 plus 3i, that would be a complex number, right? So the 7 is the real number, and the entire, you got to be a little careful here, the entire 3i is the imaginary number. But when we talk about parts, right, we would say that the 7, let me write this again, the 7 is the real part of the complex number. And then the 3 is what we call the imaginary part. The 3i is the imaginary number, but the 3 is the imaginary part of the complex number. So you have to be a little careful with that terminology. So imaginary part. And I'll just, to remind you, it's just the 3. That's the imaginary part. And as a whole, I'll do it here. This is a complex number. So in general, we can write a complex number as a plus bi, where a is the real part and b is the imaginary part. Okay, so let's do one example here. Let's say I want to express -5 plus the square root of -144 as a complex number. Okay, so first of all, I could write this as negative 5 plus, and I can break up the square root of negative 144, right? I could write this as the square root of 144 times the square root of negative 1. And we know that the square root of negative 1 is I, and the square root of 144 is 12, right? It's a perfect square. So this is simply going to equal negative 5 plus 12i. Okay, what about, here's another example. Let's say I want to express negative 6 times the square root of negative 4 in terms of I. So again, I can think of this as this is equal to negative 6 times, and I'll break the square root of negative 4 up into the square root of 4 times the square root of negative 1. But we know that the square root of 4 is 2. Remember, we're multiplying everything here. And the square root of negative 1 we write as I. So this is simply going to be negative 12i. Okay, so really the key thing is just recognizing that the square root of negative 1, we can write that as I. Okay, how do we plot a complex number? Turns out you can plot it on what's called the complex plane, which is nothing more than a usual Cartesian plane, except instead of the y-axis, think of it as like the y-axis. So plotting a complex number on the complex plane. All right, so let's say I have here, I'll get a Cartesian plane. Right, so there's my Cartesian plane. Remember, this is the draw here. This is the x-axis. And instead of y, think of this as the IY axis when we're talking about the complex plane. By the way, this is also called an Argand diagram. So this is a complex plane or some people call this an Argand diagram. So what you do basically is you plot the real part on the x-axis and you plot the imaginary part on the IY axis. So for instance, let's say the point ends up being right here. This would be the complex number 2 plus 3i. So this would be the complex number 2 plus 3i. Because the real part of the complex number is plotted on the x-axis, so that's over 2, positive 2. And then the imaginary part is plotted on the y-axis, so the 3 is plotted on the y-axis, or really the IY axis in this case. So in general, right, this would be, here I'll do it over here. Let's say this is my point. This would be the A. This is A. And then this would be the B. And then this complex number here would be A plus IB, or BI. I'll call it BI. By the way, it doesn't matter which order you write the I and the number, right? Think of it as 3 times I times 3. It's the same thing. So I'll tend to write the number in front of the I. Okay, so for example, let's do some examples of this. let's say I want to plot -4 plus 3i on the complex plane. Okay, so let's say this is my complex plane, right? Remember, again, this is x, this is I, y. So I would go -4 to the left, that's the real number part, and then up 3, right, to give me the imaginary part. So this would be the number right here. This would be -4 plus 3i. Let's say I wanted to plot, let's squeeze in another example here. Let's say I want to plot just the imaginary number 5i. Well, you can think of this as the real part is 0, right? So it's 0 plus 5i. So I would move 0 on the x, that's the real number part is 0, and then up 5 on the y, and this would be the point right here. So this would be 5i. Let's do one more. Let's say I want to plot two, right? So now it's just a real number 2. In terms of a complex number, you could write this as a complex number if you consider the imaginary part to be 0, right? So I can think of this as 2 plus 0i. So I would move 2 to the right and then up 0 on the y. So right on the x-axis, which makes sense, this is my real axis, I would plot the 2. So this is 2. Okay, or if you want to write it as 2 plus 0i, but we would just ignore the 0i and write that as 2. And then this one up here, again, would be 0 plus 5i if we write it out carefully as a complex number. But 5i stands for the same thing. Okay. So next, I want to talk about adding and subtracting. How do we add and subtract complex numbers? Okay, so adding, oops, let me go back to black. So adding and subtracting. Complex numbers. So it turns out all you have to do is add or subtract the real parts and then add or subtract the imaginary parts. Okay, so let me write that down. So to add or subtract, complex numbers, you must add or subtract the real parts and add or subtract the imaginary parts. Okay, so in general, you can think of it like this, right? So if I have a plus bi, let's say that's my first complex number, and I want to add it to c plus di, that's my second complex number. Well, the answer is I'm going to add the real parts, so I'm going to get a plus c, and then plus, I'm going to add the imaginary parts, b plus d I, and that's it. If I subtract, so let's say a plus bi minus c plus di, then it would be a minus c plus b minus d I. Okay. The other way to think about the second part right here is you can think of distributing in the negative there. So think of this piece as -1 times c plus di. So if I distribute in that -1, I'm going to get -c minus di. And then really what I'm doing is I'm adding those two together, right? So if I go back, I have a plus bi. I distributed in that -1, so now it becomes plus, and then -c minus di. Then I'm adding the real pieces. Well, what's a plus a -c? Well, a plus a -c is the same as a minus c, right? And then I want b plus a -d, but b plus -d is the same as b minus d. Right? So you get exactly the same thing. It's exactly what you would expect it to be. Okay, so for example, let's say we want to simplify this sum. So I have -8 minus 7i plus 16 minus 17i. Okay, so I'm going to add the imaginary part, the real parts first. So I have -8 plus 16, and then I'm going to add the imaginary parts. So I have -7 plus a -17. But -8 plus 16 is simply 8. And then -7 plus -17 is a -24. And I have the I there, right? So that would be the answer. So 8 minus 24i would be the answer in that case. Okay, here's another one with subtraction. So -8 minus 7i. Now I'm going to subtract this. Minus 16 minus 17i. Okay, again, I think it's easier to just distribute in the -1 and add, right? You turn a subtraction problem into an addition problem by adding the opposite. So what I'm saying is I'm thinking of it like this. The first complex number stays the same. And minus I can think of as a plus a -1, and that -1's got to be distributed in. Right, so it multiplies both of these things. So now I have -8 minus 7i. Then a -1 times 16 is -16. -1 times -17 is plus 17i. And now it becomes an addition problem, right? So I have, it's going to be -8 plus a -16, right? I add the real number parts. Plus, and then -7 plus 17. Well, what's -8 plus a -16? That's -24. And then what's -7 plus 17? That's a positive 10i. So that would be my answer. -24 plus 10i. Okay, so that's addition and subtraction. Next, let's talk a little bit about multiplication. So multiplying complex numbers. Okay, so really the way you want to think about this is multiply just like you normally would, but remember that I squared is -1. So I times I is always going to be a -1. So let me write that out. So multiply as you normally would. But remember that whenever you do I times I, right, which is really I squared, that's equal to -1. okay? And then you should have no problems if you just remember that one thing. So for example, let's say I want to multiply negative 2i times this complex number 1 plus 9i. Okay, so how would we normally do this? Well, we would distribute in the negative 2i, right? So I have negative 2i times 1, and then negative 2i times 9i. Well, negative 2i times 1, I'll do it in pieces. So negative 2i times 1, and then plus negative 2i times 9i. Well, negative 2i times 1 is just negative 2i. Right? That doesn't change. And then negative 2i times 9i, well, it's going to be negative 2 times 9, which is a negative 18. And then you have an I times I here, so that's I squared. But remember, what is I squared? I squared is negative 1. So what's negative 18 times negative 1? It's positive 18. So this is negative 2i plus 18. And then you would probably write it with the real number part first, right, as a complex number. So I'd write this as 18 minus 2i. So that would be the answer in that case. So I multiplied it just like I normally would. The only thing I need to be careful with is whenever I multiplied I times I, that's equal to negative 1. Okay. Here's another example where I multiply two complex numbers together. So multiply, let's say, 3 plus 2i times 2 minus 5i. Okay, now this might remind you of when you're multiplying two factors together, right, that are binomials. So usually we do this when we talk about polynomials in general. Then we can use the FOIL method, right? Well, you can do exactly the same thing if these are complex numbers. So I'll just say, actually, let me remind you what the FOIL method is first. So I'll say use the FOIL method. What does that mean? It means, let's say I have, I'll do it with regular linear factors first. Let's say I have like x plus 4 times x minus 3, right? So the f means the first terms. The first term in the first factor times the first term in the second factor. So that would be x times x, which is x squared. Then the o means outer, right? So this is going to be the x in the first factor times the negative 3 in the second factor. So x times negative 3 is negative 3x. Then the I means inner. So it's the second term in the first factor times the first term in the second factor, right? The inner two terms. So 4 times x is 4x. And then finally the L means the last. So the last term in the first factor times the last term in the second factor. So 4 times negative 3 is negative 12. And of course, in this case, we can simplify, we can combine like terms, like the x terms. So what is negative 3x plus 4x? Well, that's plus 1x. So I can just write plus x minus 12. So same idea as what we did there is what we're going to do when we multiply complex numbers together. Okay, and again, remember that the FOIL means first, the first terms get multiplied together, the outer, or sometimes people say outside, the inner, that's the I, and then the L is the last terms of each factor. All right, so if we go back to our problem, I want to multiply the first terms together, which are the two real number terms, right? 3 times 2. Okay, so that's just going to be 6. Then the outer is the 3 times negative 5i. Well, 3 times negative 5 is negative 15, and I still have the I there, so it's negative 15i. Then the inner terms, so 2i times 2 is plus 4i. And then the last term is 2i times negative 5i, that's going to be a negative 10 I squared. But remember, I squared is negative 1. So this is really the same as 6 minus 15i plus 4i, and then this is going to be a plus 10, right? Because negative 10 times negative 1 is positive 10. Now we can combine the real number parts. I'll write that first. So 6 plus 10 is 16. And then I'll combine the imaginary parts. Well, negative 15i plus 4i is negative 11i. So that would be my answer. 16 minus 11i. Okay, great. And I'll do more examples when we meet face-to-face in class, the 1 day per week. You guys can ask me to do more examples if you need to see more of these. All right, so we did addition, subtraction, multiplication. Let's talk a little bit about dividing complex numbers. So to divide, let me go to a new page here. So dividing complex numbers. To divide complex numbers, we need to multiply the numerator and denominator by the complex conjugate of the denominator. I'll explain what that is in a second. So we need to multiply the numerator and denominator by the complex conjugate of the denominator. Okay, so I have to explain what the complex conjugate is. So let's say my original complex number let's say it's a plus bi. Just use the most general form, a plus bi. Then the complex conjugate of that complex number is going to be a minus bi. If my original complex number were a minus bi, then the complex conjugate would be a plus bi. So you can kind of see what's going on here, right? The sign of the imaginary part is changed. So that's all you have to do. The complex conjugate is the same as the original complex number, except you change the sign of the imaginary part. Okay, so I'll say the sign of the imaginary part is changed. If it was positive, it becomes negative. If it was negative, it becomes positive. Okay, why is this useful? Well, let me explain that. So why is this useful? What's the use of the complex conjugate? Well, it turns out if you multiply a complex number by its conjugate, it ends up being just a real number. The i's disappear. So a complex number times its conjugate is just a real number. And we can see that here. I'll do it in general. Let's say I have a plus bi, right? So that's my original number. What's the conjugate of that? Well, it's going to be a minus bi. So let's expand this out. Let's multiply this out. So if I do that, right, I have a times a, that's a squared. A times negative bi, I can write as negative a bi. Bi times a, I can write as positive. You could say bai, but I could also say a bi, right? It's the same thing. Doesn't matter what order I multiply in. And then bi times negative bi is negative b squared I squared, right? But remember, I squared is negative 1. So if we simplify this further, first of all, the I terms in the center, negative abi and plus abi, they're going to cancel, right? They just add to 0. So I'm going to have a squared, and then negative b squared times negative 1 is positive b squared. Well, this a squared plus b squared, that's just a real number. There's no i's in there. So if you multiply a complex number times its conjugate, you're going to end up with a real number. Okay, so for example, let's say we want to find the product of 11 plus 2i and its conjugate. We know we're going to end up with a real number, but let's figure out exactly what that real number is. Okay, so I start with 11 plus 2i. I multiply by the conjugate. Well, the conjugate is the same thing, except I change the sign of the imaginary part, so it would be 11 minus 2i. And now if I FOIL this out, right, I have 11 times 11, that's 121. 11 times minus 2i is minus 22i. 2i times 11 is plus 22i. And then 2i times minus 2i is minus 4i squared. Well, remember, I squared is negative 1. The I terms are gone, right? Negative 22i plus 22i is 0. So this is going to be 121. And then negative 4 times negative 1 is plus 4. And that's just equal to 125. So you end up with just a real number, right? There's no imaginary part anymore. Okay, so actually let's talk a little bit about dividing now. So we started off this whole section talking about division, right? How do we divide complex numbers? Let me first start with just dividing by an imaginary number, and then I'll do a problem where we actually divide a complex number by a complex number. So in this first case, I want to evaluate negative 1 plus 2i divided by 5i. Okay, and what I want to do ultimately is I want to write my answer. I'll say write my answer in the form a plus bi, right? I want it in the regular form for a complex number. So how do we do this? Well, we have to get the imaginary part out of the denominator, right? Well, what if I multiply by, if you want, you can think of this as, you can think of it as this. Remember, 5i is the same thing as 0 plus 5i. So what I could do is I could multiply the numerator and denominator by the complex conjugate of the denominator, because I know I'm going to end up with a real number if I do that. So what's the complex conjugate? Well, it'll be 0 minus 5i. And then the numerator will also be 0 minus 5i. Okay. Now, we don't ever write the 0, so basically what you would do is you would write this as negative 1 plus 2i over 5i. You would just say, I need to multiply by negative 5i over negative 5i. You could even use 5i in this case, but I'll just keep with the conjugate. Okay, so what does this give us? Well, I need to distribute in the negative 5i, right? So negative 5i times negative 1. Well, that's going to be plus 5i. And then negative 5i times 2i is negative 10i squared. And then in the denominator, I have 5i times negative 5i, which is negative 25i squared. But remember, I squared is negative 1, right? So this is really the same as 5i. Negative 10 times I squared is negative 10 times negative 1, which is plus 10. Right? Remember, this term, this piece is negative 1, and this little piece is negative 1. Over, and then negative 25 times negative 1 is positive 25. But then, of course, we'd write this as, let me flip the numerator around. Let me write the real part first. And then we could simplify it, right? This is the same as 10 over 25 plus 5i over 25. And I can write that as 2/5 plus, and then 5 over 25 is 1/5 I. And that's what I want, right? I have it in the form a plus bi. So I divided a complex number by an imaginary number, but you can think of it as a complex number if you think of it as 0 minus 5i. So again, how did I solve this? I did my division by multiplying the numerator and denominator by the complex conjugate of the denominator, right? I changed the imaginary part of it. Okay, let's do one now where we do a full complex number divided by a complex number. So in this example, I have, say, I want to divide 2 plus I divided by negative 3 minus 7i. Okay, so remember, the way that we're going to do this is we're going to multiply the numerator and denominator, I'll put these in parentheses just to keep it cleaner, by the complex conjugate of the denominator. Well, what's the complex conjugate of the denominator? Well, the real part stays the same, so it's negative 3. I just have to change the sign of the imaginary part, so it becomes plus 7i. So the numerator will be the same thing, negative 3 plus 7i. Okay, so now I need to FOIL this out, right? So if I do 2 times negative 3, that's going to be negative 6. 2 times 7i, that's going to be plus 14i. I times negative 3, negative 3i. I times 7i is plus 7i squared. And then in the denominator, I'll simplify all this later. I have negative 3 times negative 3. It's 9. Negative 3 times 7i is negative 21i. Negative 7i times negative 3 is plus 21i. And then negative 7i times positive 7i is negative 49i squared. Okay. Remember, I squared is negative 1, right? So really I have negative 6. I can simplify the 14i minus 3i, right? That's just going to be plus 11i. They're like, think of them as like terms. And then 7 times I squared is 7 times negative 1, so that's a minus 7. I'll do one more step to find this answer here. And the bottom I have 9. Negative 21i plus 21i, that's gone, right? That's 0. And then negative 49 times negative 1 is plus 49. So now I can finally combine the negative 6 and negative 7. I get negative 13 plus 11i over, and then 49 plus 9 is what, 58? And then for my final answer, I could write that as negative 13 over 58. That's my real part. Plus 11/58. That's my imaginary part times I. So that would be the answer. So I divided, again, two complex numbers by multiplying the numerator and denominator by the complex conjugate of that denominator, right? And it was the same number except I switched the sign of the imaginary part. Okay, there's one other thing I want to talk about, and then that'll be it for this lecture. So let's talk about simplifying powers of I. Oh, I'll go back to my drawing. So simplifying powers of I. Okay, so to start, let me write out some of the powers, and we'll see if we can see a pattern here. So I'll start with I to the 0. Well, remember, just like with real numbers, anything to the 0 power, by definition, is equal to 1. So this is going to be 1. Then if I do I to the 1, remember, anything to the 1 power is just itself, so this will just stay I. Then I squared, well, we know that's I times I. What is that equal to? Well, that's negative 1, right? That's the whole bridge to complex numbers and imaginary numbers. Then we have I cubed. You can think of this as I squared times I, right? Remember the rules for if you multiply powers that have the same base, like if you do x to the a times x to the b, it's x to the a plus b, or if I go backwards, x to the a plus b, I can write as x to the a times x to the b. Same thing with i's here. You can think of I as like your x. So this is I to the third is the same as I squared times I to the 1. But we know that I squared is negative 1, so this is negative I. Then if I do I to the 4th, the easiest way to think about this is I squared times I squared. But remember, that's negative 1 times negative 1. That's 1 again. If I do I to the 5th, well, that's I to the 4th times I. So that's going to be 1 times I, which is I. If I do I to the 6th, that's going to be I to the, you can do I to the 5th times I, or I could say I to the 4th times I squared, however you want to do it. Let me just do it right as I to the 5th times I. So this is going to be, well, I to the 5th we know is I times I. This is negative 1, right? It's I squared is negative 1. And then finally, I to the 7th is I to the 6th times I. So this is negative 1 times I, which is negative I. I'll do one more. I to the 8th. Well, I to the 8th is I to the 7th times I. So it's negative I times I. Well, that's negative 1. And then, because I have the negative out front, right? The negative 1 out front. And then I times I is also negative 1. So this is 1 again. And it continues. So can you guys see the pattern here? So it repeats, right? It starts with 1, then I. So when the exponent was 0, 1, 2, 3, 4, it goes 1 I, negative 1, negative I, 1, and then 5 will be I again, and so on and so forth. So that same pattern repeats. 1 I, negative 1, negative I. Okay, so how do we find let's say I want to find I to the 47th power. Well, we could use the rules of power and try and work this out. Like we could say, well, I to the 47. Well, that's the same as I to the 46 times I. Right? Then remember another rule, you're going to need this other rule. If I do, I'll write it over here with this first rule. If I do x to the a and I raise that to the b, this is x to the a times b. Okay? So I could think of I to the 46 as I squared raised to the 23rd power. Why does it help me? Because I know what I squared is, right? What's I squared? I squared is -1. So this would be like -1 raised to the 23rd power times I. But what's -1 raised to the 23rd power? Well, it's -1 times -1 times -1, right? 23 of them. So since there's an odd number of them, you know that your answer is going to be -1, and I still have an I there times I. So my final answer is going to be -I. Well, there's an easier way of doing this. I mean, this works fine. You can break it up by using the rules of powers, but there's an easier way of doing this. Here's the easier way. Just divide the exponent by 4. So in this case, I would have 47 divided by 4, right? What does that equal? Well, it's going to equal 11, because 4 times 11 is 44, and there's going to be a remainder of 3. Now, the remainder is what's going to give you the correct answer, okay? So I'll say the remainder will give the correct answer. What do I mean by that? Well, if the remainder, let me go to the next page. So if the remainder is 0, the answer is always going to be 1. It simplifies to 1. If the remainder is 1, it's going to simplify to I. If the remainder is 2, it's going to simplify to -1. If the remainder is 3, it's going to simplify to -I. Can you guys see where that comes from, right? It comes from, if you look at the first 4 that we did. So think of the first 4 exponents, 0, 1, 2, 3, right? If the remainder is a 0, it's a 1. If it's a 1, it's an I. If it's 2, it's -1. If it's 3, it's -I. So, and then because it repeats, that will always be the case. You just have to look at the remainder. So in this case, we had, what was it? It was I to the 47th, right? So again, I did 47 divided by 4. I got 11, remainder of 3. So I look at my remainder of 3, and I know my answer has to be -I. I'm done. It simplifies to -I. That has to be the answer. Okay. Let me do another example. Let's say I want to simplify I to the, 17th. So just divide 17 divided by 4. Well, that's going to be 4 with a remainder of 1, right? If you actually did long division here, 4 goes into 17 4 times. 4 times 4 is 16, and my remainder is 1, right? So remainder 1. So now I just look at my little chart here. If my remainder is 1, then the answer must be I. So this is simply equal to I. I'll do one more. Let's say I want I to the 120th. So my exponent is 120. So I'll divide, right? 120 divided by 4. Well, this is going to be 3. 3 times 4 is 12. So now this is 0, 0. 4 goes into 0, 0 times. 0 times 4 is 0. And my remainder is 0, right? It's 30 with a remainder of 0. So what must I to the 120 be? It must equal 1. How do I know that? Because if the remainder is 0, I know that my answer has to be that first answer is 1. Okay, so that's the quick way of doing it. Divide by 4 and just look at the remainder. That will tell you the answer. Okay, great. So that's it for section 2.4. And we can get into a lot more examples and a lot different discussions in the lecture, right? When we meet group A or group B once a week for lecture. Great, thanks.